friend Adam Coates. Adam is the director of the Baidu Silicon Valley AI Lab. Adam has a deep interest in using kind of large-scale deep learning techniques, and is working right now on deep speech. He did his PhD at Stanford, and especially kind of known there for the work he did on autonomous helicopters. Adam is going to talk about bringing AI to 100 million people with deep learning. Adam.
Okay, thanks. Can you hear me okay? Did you unmute me? There we go. Oh, thank you so much, Ravi, and thanks everyone for coming. This is quite a crowd. So I want to say a little bit about the mission and kind of how I came at this. So you're hearing about personal assistants and all the ways that these are going to sort of revolutionize the way we interact with devices. This is really exciting to me because the mission of the AI lab at Baidu is to develop AI technologies that will let us have a significant impact on at least 100 million people. And so this is sort of a way of reminding ourselves every morning when we wake up to do fun deep learning things that we should choose the problems that we think will significantly affect a large number of people and try to pick the things that are most important to humans to be solved. So the first goal we've had that we think is a great enabling technology in AI is to solve speech recognition, to put speech recognition everywhere. So it turns out, especially in developing economies and in China, if you're connecting to the internet for the first time in 2016 or 2017, you're probably using a mobile device. You're not using a PC or a laptop. You're actually connecting to the internet for the first time and doing shopping and searching and reading and all of these things that I grew up doing on a PC, but you're doing it with a little tiny screen. And so something like speech recognition and dialogue systems, for example, are going to transform the way we interact with mobile devices and I think with technology in general. So for example, I think we're all ready to be able to keep our eyes on the road when we're driving so that we have hands-free interfaces and make us a lot safer on the road and be able to interact with technology the same way we interact with a passenger. I think home devices are going to finally be something that we stop walking over to have to touch all the time. We're not going to have to figure out every new microwave interface that we see because we're going to have the ability to talk to these devices and use them in a way that's natural to us as human beings. And in so doing, I think also make these technologies available and more useful to people everywhere. But one of the challenges with this that I think was looking quite insurmountable even just a few years ago is the fact that with a speech system, we could often solve very specialized problems like IVR, interactive voice response. So when you called up your bank and you had to go through a voice menu, we sort of expected that to work because it's a very narrow domain. It doesn't have to know that many words in order to be successful. But we couldn't really handle that many applications, but we could at least be accurate. And then we had more general purpose systems. So if you wanted to build something like a voice assistant, you had to be able to handle the full range of things that anyone could want to talk about. But the trouble then was that you couldn't make it accurate. And so your voice assistant would just constantly be misunderstanding what you wanted, even if it could do it for you or couldn't do it for you. And so our North Star here with trying to get speech recognition everywhere is our belief that for all of these amazing technologies to actually make it to your hands and for you to love them, we have to get speech recognition, even just the very basic building block of speech recognition, all the way to something that looks a lot like human-level performance, so that you know you can rely on it the same way you expect to walk up to your friend and be able to talk to them and have them understand you and not say, oops, sorry, I didn't hear you, every time you want them to do something. So the reason that we've ended up in this conundrum in the past is that speech recognition systems tend to be very heavily engineered. They're built from a lot of different pipelines, and this is actually standard machine learning and engineering practice. Like you take a really hard problem that you don't know how to solve, and you hack it up into small pieces that look a little bit easier, and then you try to solve each one of those as well as you can. So if you built a speech engine maybe 5 years ago, the thing that you would do is take your audio and extract a bunch of features from it that sort of represent what that audio sounds like. You would build an acoustic model, perhaps using some machine learning methods, to predict phonemes, which are kind of like units of sound that linguists have invented. And then you would try to stitch these phonemes together with another machine learning algorithm into a sequence of sounds. And then you'd have a language model and a pronunciation lexicon and a bunch of tricks inside a piece of software called a decoder, and this thing would hopefully give you the right transcription, which in this case is that I am asking, what time is it in Beijing? It's a really simple thing that I have to ask occasionally. And so with a pipeline like this, when it doesn't work very well, like your friend picks it up and they have an accent and it gives the wrong answer, it's very hard to figure out what to change. We don't know how to solve speech recognition with this system without digging into the pipeline and using our own engineering knowledge to fix it. So the way that we've improved speech performance in the past is to take all of our knowledge about the application, about the person who's talking to it, about the machine learning algorithms themselves, and trying to twiddle all of these pieces until they work better. So you can solve specific applications this way, but it's incredibly hard because our human cleverness doesn't really scale that well. So what's exciting to me is that this is a common pattern in machine learning. Very often in machine learning, we'll see that as we get more data and computation, these things will get better for a little while, and then they hit some plateau, where as you try to improve, the performance just levels off, and we have to resort to humans baking in all their own knowledge, training the users, trying to engineer the application. But deep learning has this special property that as you give someone a bigger computer and a lot more data, they can often use that to create a higher performing system. And so we wanted to use this insight to try to tackle one of these huge problems like speech recognition. So if we pour our effort in this direction into working on data and computation, maybe we can make progress. And so one of the things that you're seeing now, thanks to, I think, a lot of the work at Baidu and the speech research community, is that we are replacing the entire speech pipeline, all of those heavily engineered systems, with gigantic neural networks. And so the idea behind deep speech, which is the speech engine we've been developing at Baidu, is to try to catch up to human accuracy and make speech recognition work for everyone, not by us trying to be clever and think of everything that everyone could ever want and bake it into the system, but to focus on making these deep learning algorithms scale so well that we can close the gap with human accuracy by scalability. So deep speech is actually a fairly simple system in the end. It's actually much simpler than the systems we've built in the past. We basically take a gigantic neural network, we give it that raw audio that we used to extract features from, and we run it through a large neural network that includes a bunch of components that you can see in the research literature, and it actually predicts characters directly from the audio. And so once you have something like this that's literally predicting English characters or Mandarin characters from your audio, the hard part is now finding the best model that can fit your data and also scaling it up, finding ways to get enough data and to be able to train these models fast enough that you can actually make progress. So the real need to solve this problem is no longer engineering effort into speech recognition. It's actually sort of engineering into finding sources of data and bringing more computing power to bear on the situation. So for deep speech, one of the tactics that we took initially was to recognize that we just needed a huge amount of data. Because to learn things like how to spell in English is really hard. How do you know that knife starts with a K? And so all of these things are ones that we figured out from listening to people talk and seeing things written. And so what we did was we collected a corpus of speech data that's actually much larger than any of the speech corpora you see in academic work. So a very common data set called Fisher, who's about 2,000 hours of training data. And the first training set we used with deep speech was something like 12,000 hours. So there's like a factor of 6 right there increase in training data so that we can just learn as much as we need to learn about the language from the audio data. But it turns out that even this isn't enough, and this is where we start needing to get a little bit clever, but in a different way than we have in the past. So there are many kinds of distortion that we care about. Maybe it turns out that the kind of audio we're hearing is very reverberant, or it has noise, like I'm trying to use my phone in a cafe. Maybe there's far field because this is a home device and you're standing across the room. It could be that there are changes in tempo, because once you're able to chat with your speech recognition system, you start to get excited and you talk really quickly and you put all this emotion into it that is not in your training data, because that's people reading books to you. And so instead of trying to engineer these things to account for all these little scenarios the way we would have in the past, what we do now is we think about how can we engineer the data? How do we go out and find demonstrations of these phenomena so that the system can learn to be robust to those things on its own? So what we can do is actually take this raw audio that costs money to collect, and we can augment that data, and we can actually generate new data that is just as good as far as training data goes, but represents the things we want the system to learn. So as an example, I want to show you how we do this for something like far-field speech. So here's an example of an audio clip of someone reading like a news or technical report to us.
Home's new lines of insurance carry higher than average risks, some analysts say.
So this is someone talking about insurance, so not surprisingly, it's not super exciting. If there are any insurance folks out there, maybe you're really pumped about speech recognition coming to insurance. But what we can do, if we're interested in this working in like a far field scenario, is we can take a representation of how audio reflects inside a room like this one. And we can convolve this with the audio to create something that sounds like far field speech.
Home's new lines of insurance carry higher than average risks, some analysts say.
So this actually sounds like someone speaking in a hall like this one or in a large room that doesn't have carpet. And this is a fairly straightforward thing to do. And now I'm going to play you a piece of real far field speech that we actually recorded in a room kind of like this one over at Baidu.
Play NSYNC's top song.
So this is actually something you might want your system to be able to do, is hear someone say, play NSYNC's top song from across the room. And it actually sounds very similar. It's got that same reverberant quality because that's the way some rooms are built. And it turns out that if you do this, you can slash the number of errors you make in these scenarios by something like 15 or 20%, which would represent a massive gap to have covered if you were trying to engineer the system by hand. And it's only by just demonstrating to these deep learning systems what the world is like, rather than trying to use our own knowledge to solve that problem. So to actually make this work, it's not enough just to be able to synthesize lots of data. You've also got to be able to search over models very quickly to find one that'll fit it, and you have to be able to handle large-scale training. And that's one place where our team has specialized a lot, because by the time these systems are done, they will have seen something like 30 years of spoken audio total. They will have heard more speech in their ears than any human hears in their lifetime. And so to train on data sets of this size, you need huge amounts of computing power. And you need not only to go quickly, but to do it very quickly so that you can run lots and lots of experiments. So one experiment for this system that we're talking about takes 10 exaflops. I think that's 19 zeros after that. So on a 6 teraflop GPU that you could have bought last year, this is like 3 to 6 weeks for one experiment. So if you want to find that best model that fits your data and works really great for far field speech, that's wonderful, but you better be willing to wait 6 weeks every time you try something new. And that won't work for your development team. So I won't go into details on how we do this, but we've actually put a huge amount of effort into developing software packages, some of which, like one called Warp CTC, are available to developers out there to cut these training times down. And in fact, you can run these experiments in something like 3 to 5 days now on dozens of GPUs. So one of the cool things about this is that we don't just have the ability to create new data sets and get our system to generalize to different kinds of English speech. We can actually swap out whole languages without changing the algorithm much. So for example, we put in some English training data at the bottom, and we ask the system to create English transcriptions. There's nothing fundamental about English in any of the diagrams that I've shown you, and it really is as straightforward as swapping in Mandarin data and giving the system a Mandarin transcription and asking it to predict Mandarin text. And so even though Mandarin is very different from English, I really mess this up every time when I travel to China. I can't get any of the tones right, and no one knows what I'm saying. But this system can actually learn to handle a totally different language system without many changes. All we have to really do is change the character set. And what's exciting to me is that we're in this place now where if we want to reach 100 million people, We don't just have the ability to project ourselves in terms of copying software and creating things that solve specific problems. We can actually create a system, a single algorithm that learns to serve people in another language when even I cannot speak that language or understand it myself. And so one of the really exciting things about this sort of approach is that you can even learn things that I have no equivalent for in English. You can learn things like hybrid speech. You can learn that people have used like brand names. So for example, if I'm saying my favorite singer is Angela Baby, who's a famous musician and movie star in China, this is something that the system can actually learn that this is an English word, switch character sets, and output the correct transcription, even though there's not a single engineer on our team that bothered to put that in the system. It's just in the data, and so the system learns to handle this hybrid case on its own. So does this actually make things more efficient? It absolutely does. And one of the things I'm really excited about from last year is that we participated in a study with Stanford and UW that showed, in fact, that typing compared to speech input there's a huge gap in performance there. That speech is not just a little faster, it's like 3 times faster than typing, even when you account for all the corrections. And so you can see these little box plots. The blue and the red box at the bottom are the words per minute for typing on a keyboard. And those other 4 box plots are the fact that we can run 3 times faster when we're typing in both English and in Mandarin. But here's the one that really excites me, is that for English, it turns out that the number of errors that you make once you account for people trying to correct things doesn't really change. It's actually more accurate, slightly more accurate in English, because the speech engine makes fewer mistakes than people make typos. But in Mandarin, it turns out that users using keyboard make vastly more mistakes than when they use speech recognition. And there's a huge variance on the number of mistakes that they make. And the authors hypothesize that the reason this happens is because typing in Mandarin is really complicated, and every keyboard is a little bit different, and it has to do with your education level and all these crazy things. And so just to use your phone, which is the first connection you've ever had to the internet, you have this giant gap in skills from the very beginning, from the time that you pick it up, because that is your only way to interact with it. And so now with speech recognition, we see that that gap closes. That with speech recognition, this is a system that's now accessible to everybody. And I think that's incredibly exciting and goes to our ability to affect a very large number of people in a powerful way. So I think in addition to this, you're going to hear a lot about assistants today and other technologies, but I think speech in general is letting us rethink all of these product experiences and really help bring AI to people. And if you want to play around with this in English, you can head to talktype.baidu.com and play around with the English version of the deep speech engine, which isn't quite as strong as the Mandarin version, but I think has really changed my own habits, because I kind of know I can trust this thing to type the right thing now. So I'm incredibly excited about this. I think deep learning is allowing us to finally close that gap with humans on speech, and to do it in a very scalable way. And I don't see that stopping. There's still more to do, but as we get more data and computing power, this is going to keep getting better. And I think that's incredibly cool. And the second thing is that speech is already enabling this proliferation of new products. We're going to be able to have home devices and so on that we can interact with in new and simpler ways. And the one thing that I think a lot about at Baidu, and I hope everyone working on these products will think about, is that we really want to make these work for everybody. And I think in a very special way, AI lets us do that for the first time. Thank you.